Hello everyone, my name is Duan. Today I would like to talk about our latest research work, Pangolin, a comprehensive framework for testing configuration-rich key-value store. So modern key-value store are widely used as the persistent storage layer for the search engine, distributed file system, blockchain, data analysis engine, social media, distributed database, and so on. However, can key-value store be bug-free? Probably not likely, because modern key-value store have massive code base with very complicated functionalities. The table shows the five widely used key-value store, the length of code, API functionalities, the number of configurations, the version released since 2015. So you can see the studied modern key-value store are very complicated with the code base. So before we jump into some detail about today's presentation, I just want to briefly talk about the outline. First of all, I will cover the historical bug study about the bug reproduction, bug pattern, bug funding approach. Second, I will talk about the system design and the implementation about the Pangolin, a generic architecture for black box testing and fuzzing. It is also have the grammar-based test case generator with fine-graded boundary. Finally, I will talk about the evaluation to cover the effectiveness, efficiency, and overhead for finding bug by using Pangolin. So, about the historical bug study, we performed the historical bug study for the five widely used key-value store. Those are RocksDB, LevelDB, HyperLevelDB, BetterDB, and Redis. We totally inspected 224 historical bugs during the past 9 years, from the 2015 to the 2023. The bug is referred from the patches, versions, bug reports, issues, and the developer forum, and so on. So the goal for the bug study is we try to answer the research questions. First, what consequence does bug causes? How to trigger or reproduce bug? What bug look like regarding the configurations and operations? How were bugs found? So for the bug consequence, we classify the bug consequence into seven types, fall into the two categories, memory bug and semantic bug. So we can find the bug consequences are very diverse in all five studied key-value store. Unlike a bug consequence, we also find the bug reproduction, the synthetic system crash and operation sequences can reproduce most of bug. Actually, more than 70% of bug can be reproduced by these two types. For the bug pattern, first, we find a small number of unique operation configuration can reproduce most of bug. For example, the max number of configuration in the test cases is 4. The max number of unique operation is 6 to reproduce all historical bugs in the studied key-value store. Second, configuration-related bugs have become a serious issue considering more and more configuration is introduced. So more configuration introduced, more configuration-related bug will show up. Last one, manual tests are inadequate in finding bug. However, there is a lack of using the general tools such as fuzzing and black box testing. So why there is few testing to use for the for targeting the configuration-rich key-value store? There are two reasons. One is configuration-rich key-value store are very complicated in syntax and semantics. Unlike the circle in DBMS and the POSIX in Linux, the configuration-rich key-value store is lack of a standard. for regulating key-value store specification, so it is difficult to gear the general testing tools such as fuzzing and black box testing to targeting key-value store. The second reason is, more importantly, the modern key-value store has large test spaces regarding to the number of configurations. Large configuration exponentially increase test space. The table shows the number of configurations used for the file studied key-value store. So the consequence is the large test space causes high storage and computation overhead for targeting for using the fuzzing and black box testing, and make those testing to very low efficiency. So in this paper, we present a generic architecture of fuzzing and black box testing for efficiently targeting the configuration-rich key-value store. The figure shows the general overview and the workflow of the black box testing and fuzzing. So we provide a generic architecture. That's the uniform grammar-based test script, specification descript for fuzzing and black box testing. Also, we provide a bounded test strategy with fine-grained boundary. So this approach is in effect by insight from the historical bug, in which most of the bug can be found by systematically testing small sequences of operation and configurations. So what is grammar-based test? So we try to generate the test cases that syntactically valid test cases by using the kvdb command. Then we try to generate semantically valid test case by figure out the key-value store specification into the kvdb metadata rules. So we can generate both semantically and syntactically valid test cases. These test cases fit for both fuzzing and black box testing. So how to shrink the test space? We can define the test space as the number of configuration and operation involved in the test cases. So based on the insight from our historical bug study, in which most of the bug can be found by systematical test small sequences of operation and configuration, we can bound the test space. However, how to figure out the boundary? One way is use the coarse-grained test boundary to cover all historical bugs by using this coarse-graded boundary. But we can go further by using the fine-graded test boundary that just cover all historical bugs regarding to the configuration and operations. So you can see it can significantly decrease the test space. And also, this approach can be an incremental test pattern to avoid historical bugs that recur in newly released version of key-value store. The fine-grained boundary of the file study key-value store we provided in our research work. This figure shows the overview of the system design, implementation, and the workflow of Pangolin. So you can see there are several shared components and files, including fuzzing seed, test case, key-value store interpreter, and the kvdb checker. The input for the Pangolin is test boundary and the target key-value store specification description. That's the kvdb grammar. Output is the bug report. So for the evaluation, we try to answer the three research questions. One, how effectively is Pangolin in detecting bugs? Second, how much compute and storage overhead is incurred in Pangolin? Third, what efficiency and effectiveness does the grammar-based test case generator with fine-graded boundary have? So for the first research question, Pangolin found totally 20 new bugs in the study 5 key-value store, including memory bug 8 and semantic bugs 12. Here is one bug case study in RocksDB memory bug. For the what effectiveness and efficiency does grammar-based test case generator with the fine-grained boundary have? First of all, for the blackboard testing, you can see all new bug and historic bug are found within the fine-grained boundary. Also, it is efficiently shrink the test space exploration for finding new and historical bugs, significantly decrease the overhead. So for how much computation and storage overhead required in Pangolin, so for the blackboard testing, you can see 2 to 15 times shorter in computation, 2 to 15 times smaller in storage compared to the general blackboard testing. For the fuzzing, so the figure shows the cumulative code bus coverage of Pangolin. The more code bus coverage than the traditional grammar-based fuzzing Nautilus and feedback-oriented fuzzing AFL. That means Pangolin can find more code bus and cover more code. So contribution. We present a comprehensive study of the historic bug in 5 widely used key-value store, a bounded test strategy with a fine-grained boundary, a generic grammar fuzzing and blackboard testing framework Pangolin, experiment evaluation. Thank you so much.